70% of the Earth's surface. They not only serve as the planet's largest habitat, but also help to regulate the global climate. The ocean is a continuous body of saltwater that surrounds the continents. It is divided into 4 major regions: the Pacific, Atlantic, Indian, and Arctic. The ocean contains traces of all chemical elements found on Earth, but it tastes salty because of sodium and chloride ions in rainwater runoff and minerals from geothermal vents on the seafloor. Climate change is altering the ocean in 3 major ways. First, the ocean is getting warmer. The greenhouse effect not only warms the planet, but also raises the temperature of the world's oceans. Over the past century, the ocean's surface temperature rose at an average rate of about 0.13 degrees Fahrenheit per decade. And during the past 30 years, sea surface temperature has been consistently higher than at any other time on record. This warmer water vaporizes quickly, fueling stronger and more frequent storms. Higher temperatures also threaten delicate ocean life like coral reefs and disrupt the food chain, from krill to penguins to seals. Second, since 1993, the seas have been rising at a rate that's twice as fast as the long-term trend. Sea levels rise not only because water expands when it heats up, but also due to melting glaciers and ice sheets. Rising seas contribute to flooding on once dry land in coastal regions. A third consequence of climate change is ocean acidification. Seawater absorbs CO2 from the atmosphere, which lowers its pH and results in higher acid content. This reduces the concentration of calcium carbonate, which makes it difficult for species like oysters, clams, and corals to form shells or skeletons. The only way to stop the damage to our oceans is to dramatically reduce greenhouse gas emissions. But even if emissions stop tomorrow, the gases currently in the atmosphere would take decades to dissipate.
This lecture will cover the topic of climate change in our oceans and Earth's atmosphere. So you just finished watching an introductory video of how climate change affects the oceans. So today we're going to go into a little more detail of how that works. What are the natural long-term changes in Earth's climate that we've observed in the fossil record and in the ice core record? And what are the rapid scale changes that we see today, and how do we know that these changes are caused by humans? So the past decade, from 2010 to 2020, has seen an astonishing run of record-breaking storms, forest fires, droughts, coral bleaching, heat waves, and floods around the world. And this is just with 1.8 degrees Fahrenheit, or about 1 degree Celsius of global warming. So today when we look at climate mechanisms and we look at how humans contribute toward climate change, keep in mind that from what we've seen in the past decade, we're only talking about 1 degree Celsius of change has caused all of these effects in the span of 10 years. So keep those numbers in mind when we think about how Earth heats up or cools down. We need to know how fast that's occurring, right? So natural long-term changes in Earth's climate occur over very long periods of time, millions of years, whereas the climate changes we see now are on the short term. So first, let's start off with how do the long-term changes in climate work? And how are they different to the rapid changes that we see now? So here I have a diagram illustrating Earth's climate system. So after the past couple of weeks, you guys are a lot more familiar with how different temperatures of ocean currents and speeds of ocean currents leads to climates in specific zones along coastlines of various continents. And you've seen how slight changes in atmospheric composition affect ocean composition. And so when we think about Earth's climate, we have to think of it as a complex, multi-linear, exponential system, right? Climate is the result of the interactions of both the ocean and the atmosphere. So the Earth is constantly in motion, interacting one layer with another and causing changes in another. So you can see here all of the various ways that biology interacts with the atmosphere, the way that the atmosphere interacts with the amount of global sea ice, how you get changes in solar inputs will cause changes in atmospheric circulation. All that stuff is interconnected, and one change will directly cause another. So if we look at Earth's history over the long term, down here I have something called the geologic time scale. So it's like a way to measure geologic time. So here you can see it's measured in millions of years ago. So here we are, present day, and then all the way over here is 542 million years ago. So 542 million years ago, that's around the time that macroscopic life was very prevalent on the planet, right? Before this time, it was more, it was limited, right, to bacterial life forms and single-celled life forms. So Earth does experience natural long-term climatic cycles, which are known as Milankovitch cycles. And these natural cycles are a result in the variations of the tilt and precession of Earth's spin axis. So these changes are measurable, and we can expect them to happen at regular intervals based on measurable astronomical phenomena. So because of Earth's axis's periodic change in eccentricity and precession, Earth basically fluctuates back and forth between two states, right? Glacial periods and non-glacial periods. So the blue here indicate glacial periods in Earth's history. The white periods indicate warm periods, right? Or we also call them greenhouse or tropical periods. So each period, this is very important, each glacial period and each warm period lasts millions of years. So you can see here, this warm period lasted for about 100 million years, and you've got another cold period lasting for, roughly another 100 years or so, 100 million years, sorry. So we can see that the changes that do occur naturally occur over long periods of time, right? Earth doesn't transition from a hot climate to a cold climate overnight from only Milankovitch cycles, right? These natural cycles take a long time because of the length of their period or their cycle. So here is a diagram of what Milankovitch cycles represent, right? They're the result of three different natural changes in Earth's orbit, so the eccentricity of Earth's orbit. So you can see that Earth oscillates back and forth regularly, measurably between a circular orbit and a slightly elliptical orbit. And so it oscillates back and forth between these two every 23,000 years, like a clock. Another natural change that occurs over a long time span is the change in the obliquity of Earth's axis. So remember, we talked about how Earth's axis is tilted, and that's why we have the seasons. So right now, Earth's axis is at about 23.5 degrees, but that oscillates back and forth over 41,000 years. So you may see it as low at 22 degrees at some points, all the way up to 24.5 degrees at some points. The third natural Milankovitch cycle is the precession of Earth's axis. So this is a little bit harder to visualize, but you can see here relative to the North Star. Oops. You can think of the precession as being like a spinning top, right? Earth's axis precesses on a period of 100,000 years. So we can graph that and see what they look like. So here's the period of eccentricity, of obliquity, and precession. And as you can see, these curves are regularly periodic, which means that we can predict when Earth will go into an ice period or a warm period based on where these curves intersect. Where you have multiple curves overlapping in a maxima, you'll have a warm period. Where you have multiple curves overlapping in a minima, you'll have a cold period. So we've been able to trace this, as you saw from the previous slide. We've been able to trace this going all the way back to the Cambrian period, 542 million years ago. So because of these Milankovitch cycles, Earth oscillates over millions of years between cold and warm states. So how do we know that, right? It seems like an incredible thing for scientists to know, and it's actually really fascinating how this was discovered, was using something called the ice core record. So other things are used as well, such as corals, glacial ice rings, tree rings, pollen, even sometimes historical documents can be used to corroborate data. But the major one, right, the major way that scientists measure ancient climate is through the ice core record. So I've got 2 videos on this that explain how this works. But in a nutshell, scientists drill through the ice and then they bring up these cores. And inside these cores, there are trapped air bubbles. So you can think of this ice you can think of those air bubbles as being fossils, right? So the deeper they drill into the ice cap, the older and older snow they're encountering, right? Snow that was precipitated a longer and longer time ago. Whereas at the at the surface here, you have the youngest snow. So if they're interested in seeing how climate has varied through time, they drill through the ice sheet and then look at it from the bottom of the core to the top of the core and see what changed along the length. And so in this core, there's lots of little air bubbles. And when those air bubbles were frozen in to the ice, they became locked. Right, so the air that's that's trapped in those bubbles is a fossil of what the atmosphere was like when that ice formed. So you can think about it like the mosquito in the amber of Jurassic Park. Right, the mosquito is like the air bubbles; it's preserved, and then the scientists come along later and they sample it and they take the mosquito blood out and they make the dinosaurs. So let's have a look at this video here, where you can see that in action.
At the National Ice Core Lab in Lakewood, Colorado, a giant freezer stores over 45,000 feet of ice, drilled from 34 sites around the cryosphere. Dating back hundreds of thousands of years, these ice cores are time capsules that allow scientists like Jim White to peer deep into the history of ice.
This piece of ice is interesting because it has a couple of things you can see right away. One is there are bubbles throughout here. These bubbles are little packets of air. It's these bubbles we can take out and measure CO2 and methane and nitrous oxide. It's the only medium that really collects the atmosphere itself. The other thing you can see in here quite clearly is you can see the layers. And the thickness is going to tell you how much snow fell that year. So you get a couple of pieces of climate information and a dating scale just out of visually looking at this ice core.
Most importantly, scientists have identified a direct historical link between increases in greenhouse gases like carbon dioxide and steep rises in global temperatures. At every peak, big rises in sea level followed as Greenland's ice sheet shrank. The ice core records also reveal a particularly telling moment in Greenland's history. Roughly 125,000 years ago, temperatures rose by about 7 degrees Fahrenheit. The entire southern portion of the ice sheet melted, and global sea levels rose by over 10 feet. It was caused by a change in the Earth's orbit around the Sun, which increased temperatures and released carbon dioxide from the oceans. The more recent ice core record shows the potential for a similar meltdown. Right now, greenhouse gas levels in the atmosphere are even higher than they were 125,000 years ago, higher than they've ever been in the last 500,000 years. Temperatures are already following suit. The only explanation is the burning of fossil fuels.
What we see in this ice core is very solid evidence that what's happening today in the atmosphere is different. It's not a normal part of the climate cycle. It's something caused by human beings.
Rising temperatures are once again pushing Greenland towards a major meltdown. But what the ice cores can't tell us is how long it will take. The last time Greenland lost a significant portion of its ice, White suspects it happened over thousands of years. But this time, it could happen much faster.
This is our climate. What do I mean? Most of us have heard of the ice ages from movies. Everybody down! 20,000 years ago, places like New York City were covered in ice. But that wasn't the only time. There were a bunch of ice ages, going back millions of years. And here's the crazy part. By looking at cores of mud from the bottom of the ocean, we can tell that these ice ages actually came and went on a schedule, like clockwork. In fact, the entire world got hotter and colder with the ice ages. So what caused these huge swings in Earth's climate? Actually, it was clockwork, corresponding to slight shifts in Earth's orbit, now called Milankovitch cycles after the Serbian scientist who started to figure this out. We know that the gravitational pull of the sun, moon, and other planets makes the Earth's axis wobble like a top on a cycle of about 20,000 years. The tilt of the Earth also shifts about every 40,000 years. And the shape of Earth's orbit around the sun goes from more circular to more like an oval on a schedule of about 100,000 years. All of these changes affect how heat from the sun warms the northern hemisphere where ice sheets can grow. So, the same types of planetary movements that create our days, weeks, and years actually seem to also create something like superseasons, our climate. But that's only part of the story. Because with the orbital cycles, when the northern hemisphere warms, the whole planet warms. And when the northern hemisphere cools, the whole planet cools. Changes in Earth's position set the tempo of the climate clock, but they don't explain why the shifts in temperature are so extreme and why they're global. Going from times when New York City could be covered in a thick layer of ice to times like today, when it hits 100+ in summer. So what else is going on here? A major clue came when scientists extracted cores of ice from Antarctica, dating back hundreds of thousands of years. And inside of them were trapped little air bubbles of ancient atmosphere. They revealed the amounts of carbon dioxide in the atmosphere going back 800,000 years. Remarkably, the rhythm of this record matches that of the ice ages recorded in the ocean muds, almost perfectly. We know that CO2 is a greenhouse gas, a gas that traps heat on the planet. So this could explain those huge global shifts. But where did the CO2 come from? Why would gas in our atmosphere match the tilt and wobble of Earth? This is where that can of soda comes in. These are carbon dioxide bubbles, now visible because I just depressurized the can of soda. One theory is that as the ice sheets melt, they release pressure on the world's volcanoes, setting them off like a freshly opened can of soda. But that can only account a little bit for what was going on. Another theory is that the oceans act like a sea of soda. How do I get a ton of bubbles to come out? By stirring it up. The same thing happens with the world's oceans. They also contain carbon dioxide. And our planet, the blue marble, is 70% ocean. Now, even though a can of seawater doesn't have quite as much carbon dioxide as a can of soda, that's still a lot of carbon dioxide in all of the world's oceans. And when ice sheets start to grow, that changes everything. The wind patterns change, which shifts ocean currents, and that changes how the ocean mixes. Scientists believe that the biggest reason CO2 tracks the orbital cycles is because when the planet warmed just a touch, that enhanced ocean mixing. And then just like our stirred soda, the oceans lost some of their fizz to the atmosphere. And more CO2 in the atmosphere meant more heat trapped on the planet. But today there's another source of carbon dioxide. Every year, humans dump over 30 billion tons of carbon dioxide into the atmosphere. That's well over 50 times the amount that comes from volcanoes. As a result, we're warming the planet 10 times faster than anything we've ever seen before. The tight link between the orbital cycles and the atmosphere is gone. We've actually broken the climate clock.
So now we can look at the ice core record. And for a long time, there wasn't an availability of a continuous core that would extend back 800,000 years. And so there was criticism, around 50 years ago. And so scientists started to do more extensive drilling on multiple continents. And then we're finally able to corroborate all of the ice core data together into a theory. So here we can see we have this ice core record that extends back to, 800,000 years ago. So notice there's three different things being displayed here. There's a red curve, a green curve, and a black curve. So the black curve indicates temperature of the planet. The red curve indicates the amount of carbon dioxide present in the atmosphere at that time from the bubbles in the ice core, and the methane in green. So what you may notice about these curves, just looking at them from first glance, is that they look very similar, right? So that's not a coincidence. They are directly related. A change in one causes a change in another. So you can see here they parallel each other. When one goes up, the other goes down. When one goes up, the other goes down. So if you increase the amount of carbon dioxide in the atmosphere, you will, as a byproduct, increase the amount of temperature and methane. So we're going to talk about this today, how that works. It's called a positive feedback loop, right? One thing affects another thing. However, what you saw in the last two videos was this scary image over here at time 0, right? This is 2020. And we can see here that carbon dioxide and methane have skyrocketed. So there's no gradual curve here. You can see they're forming this straight line seemingly to infinity. But temperature is still down here. But we know that eventually temperature will mimic that, and it will come up and skyrocket in the same way. And we're already seeing those changes occurring today. So over here, this is very important for you to know exactly what this is. So carbon dioxide in parts per million. So this is how much carbon dioxide is present in the atmosphere. And for your reference, the safe limit for humans is 350 parts per million. So anything higher than 350 ppm CO2 is hazardous to human health. So here you can see the arrows are above 350. Right now, the current concentration of CO2 in our atmosphere is about 410. So we're already breathing about 60 parts per million over the safe limit. And that keeps increasing at an exponential rate. And so you can see that blown up here, right? So they zoomed in. So we're now no longer looking at thousands of years before the present. Now they're showing a diagram that's only zoomed in to years before 1950. Right, so here we are. You can see here's 500 years ago, 1,000 years, 1,500 years. And so you can see it's a pretty flat curve until around, I'd say about 100 years before 1950, around 200 years before 1950, it skyrockets, right? And it forms this scary picture here. So we're going to look at that and talk about this is a result of human activities here. It doesn't match with the Milankovitch cycles, right? Milankovitch cycles take place over millions of years to warm a planet. It doesn't take place over the span of 10 years, right? So when we talk about global warming, you know, I'm sure you guys are so nauseatingly familiar with the misinformation of science that floats around on the internet, especially in the time we're in right now with this pandemic. There's so much bad science and misrepresentations of truth that the public is confused. So you've probably heard lots of different things before, like Earth has been warmer in the past, and that's true, right? We can see Earth has been warmer in the past, but it's never gotten this hot in such a short period of time. And because of that rapid rate of change, it triggers some pretty catastrophic consequences for the survival of the human race. So if we want to look at the idea of global warming as a basic concept, you guys should all understand something called the greenhouse effect. And if you can learn the greenhouse effect, you will be smarter than probably 80% of American voters. So climate change is explained very simply by Earth's natural mechanism called the greenhouse effect. So in Earth's atmosphere, you can think about Earth as being a greenhouse, and the ceiling of the greenhouse is Earth's atmosphere. Solar radiation is allowed to come in through the ceiling of the greenhouse or in through Earth's atmosphere. That solar radiation is then absorbed by the ground, and the ground converts it and re-emits it as heat. And heat actually cannot escape through the atmosphere. So once the ground converts it, that heat actually gets trapped inside the greenhouse. So that's why greenhouses are very warm and cozy, and that's why Earth is also very warm and cozy. Based on Earth's position in the solar system, where Earth sits relative to the sun, its average temperature should be 0 degrees. It should be frozen over, but it's not because of the greenhouse effect. That's what keeps our planet nice and stable, is because of that effect and these greenhouse gases. So there's a very small proportion of these gases called greenhouse gases that trap heat on our planet. It keeps it from escaping. So normally Earth has something called a heat budget, which means that it has a natural balancing act between the incoming solar radiation and the emission. And so Earth has to keep that budget in place. Otherwise, you will create something called a tipping point. And so you'll get a cascade warming effect if that balance isn't maintained. So think back to our lecture on ocean-atmosphere interactions. We looked at a pie chart of what Earth's atmosphere is made of, and it was mostly oxygen, nitrogen, and we had a small amount of these things called greenhouse gases. So water vapor is a big one. Carbon dioxide is another. and the third and the most powerful is methane. So in this lecture today, I'm going to talk about how humans have altered the amounts of these greenhouse gases in our atmosphere and how that change has created this cascade global warming effect. So let's look at this famous curve here. So this curve comes from the famous father and son team from the observatory in Hawaii. And basically what this curve is showing is here on the x-axis, we have the year, right? So here's the year 2000. And then on the y-axis, we have the amount of carbon dioxide, right? The greenhouse gas in parts per million. So remember, 350 is the safe level for humans to breathe. So we see this first sharp increase in the curve around 1750. And if you've ever taken a history class, you'll know that that was the start of the Industrial Revolution, where humans started to burn coal and other things to expand their workforce and their economy. And, you know, you can't fault the humans at the time because they didn't know the effects of that, right? Science was very limited in this time period. And it wasn't until in the 70s, 1970s, that scientists found out this link between human activities and the change in climate. So you know, humans are very resilient and adaptable, and you know they spawn this great you know, transition into a world of global economy and transportation. So that effect can be directly observed in the CO2 record. So this father-son team were the first to demonstrate that and connect it with the Industrial Revolution. So let's have a look at some of these greenhouse gases, right? So remember, let's just go back here to the greenhouse. Carbon dioxide is a greenhouse gas. Methane is a greenhouse gas. So the more of those gases you put into the atmosphere, the stronger your ceiling, right? The stronger the top. So you can think about adding CO2 to the atmosphere is the equivalent to adding more glass panes on the roof of your greenhouse, right? It's very simple way to explain it. So a lot of people think that, you know, you have to understand very complex climate projections to understand what's occurring, but it's not. You don't. All you need to understand is the components of our atmosphere and how they work together with our planet and how different changes will affect heat flow and Earth's heat budget. So let's look at some of these and how human activity affects that. So you guys are probably very familiar, obviously, with the combustion of fossil fuels, right? You all put gas in your cars. I mean, I guess unless you drive an electric car, but the majority of people are driving fuel cars. And so the combustion of fossil fuels before the Industrial Revolution was about 280 parts per million. The present concentration, it says here about 387, but I mentioned that it's around 410 now, right? This diagram is a little bit old. You can see that's from 2011. So in the past 9 years, the amount of CO2 has obviously increased. Then we also have methane. This is a big one. And next week, you're going to watch a documentary called Ice on Fire. And they talk a lot about how humans are contributing a lot towards the increase in CO2, but a lot of the time methane is overlooked, right? So this is a huge one because methane is such a stronger greenhouse gas. Right? It's something like 10 times more powerful at trapping heat at the Earth's surface than carbon dioxide. So methane comes from, the main source is actually from cattle and the beef industry. So there's a lot of different ways that humans have contributed to climate change. It's not just the burning of fossil fuels and putting gas in your cars. There's a lot of different ways. So I have this video here. It's a really great illustration, since I can't draw on the board and show you how this works. It's a great illustration of how humans disrupted that natural climate cycle through those types of activities.
The Earth has an elegant cycle of life. It's the story of carbon, and over billions of years, it has evolved to look something like this. It starts with a plant. Plants and microorganisms absorb carbon dioxide from the atmosphere. Then, they use energy from the sun to convert that carbon into oxygen and sugar, which they use to grow. And as they grow, they emit some carbon back into the atmosphere. But all plants eventually die, and some are consumed by bacteria, others by larger beasts. These animals eat plants for energy, and they breathe out carbon. But eventually, those animals die too, and they end up in the ground. Meanwhile, a similar thing happens in the ocean. Coral and plankton need carbon from the water to survive. Luckily, the ocean has carbon because it absorbs some from the atmosphere. And when rain falls to the earth, it grabs some carbon from the atmosphere and from rocks and flows into the ocean where the coral and plankton use carbon to grow, or other animals use it to grow. But just like animals, the coral and plankton die too. In short, all living things are made of carbon, and they eventually end up in the ground. Some of that carbon will eventually get back to the atmosphere, but some of it normally stays in the ground. Usually, dead things decay and turn into rocks. Eventually, they are crushed, and the extreme heat and pressure causes them to melt and emit the carbon, which is trapped underground. Over time, that trapped carbon eventually escapes into the atmosphere when volcanoes erupt, and the cycle starts again. But occasionally, dead plants and animals don't turn into rock. They don't decay fast enough, so they turn into oil, coal, or natural gas. This carbon gets stuck in the ground. This is the elegant system that keeps carbon cycling through Earth at a steady pace. Carbon in the atmosphere keeps some heat from leaving Earth. It keeps Earth at a stable temperature. But very recently, one of these animals started to dig up the carbon in the ground. They took the carbon that was stuck in the ground and put it back into the atmosphere. And they did this so much in such a short time span that the cycle was disrupted. Too much carbon was being put into the atmosphere. Heat that would normally be able to escape bounced back and stayed on Earth. And Earth started to get warmer and warmer. Really recently, just a few months ago, more than 100 bipedal scientists said they might only have 12 years to stop a disastrous amount of warming. So these animals not only need to stop putting carbon in the atmosphere, but also get carbon out of the atmosphere. They found one way to remove carbon is to grow more plants. They could stop cutting down trees or raise livestock in ways that help restore grass. Another way is to let plants suck up carbon from the atmosphere, but then burn them for energy, and then trapping the carbon they emit underground. They could also build machines to suck air from the atmosphere and filter out the carbon, but they haven't figured out how to do this fast enough. There are many ways these animals can tweak the cycle to suck carbon out of the atmosphere. A combination of them is probably the best way forward. But first, these animals need to figure out how to stop putting it there in the first place. If you haven't heard already, we've launched a paid membership program on YouTube called the Vox Video Lab. For a small payment, you have access to some amazing perks, like access to live streams with our creators and a little badge that appears.
That's why oil is called fossil fuel, right? It's actually from fossilized animal and plant remains that have been buried and pressurized for over millions of years. So that's also the reason why there is not a fixed amount right? So someday we're going to run out of oil, and that day is very soon, right? We only have Earth only has about 50 years left of oil, but it's likely that we'd have to switch over much sooner than that to preserve the planet. Okay, so we're looking here at the ice core record. Right, so remember, when we look at changes, we're looking at the rate of change. How fast, by how much is something occurring over a period of time. So that's how we measure the severity and the impact. But, humans have never observed anything like this before. So it's really important that all of our best scientists continue working on this. So we know that the 8 warmest years on record have occurred since 1998, and actually the past 5 years from 2015 to 2020 were the hottest on record of all time for human history. So Earth's surface temperature, it's really important to keep that in mind, has only risen 0.8 degrees Celsius in the last 140 years. So when we talk about all of these catastrophic changes that are occurring, that's from only 0.8 degrees Celsius. So you have to start to think about these numbers in a different way, because if you don't understand the scientific meaning behind that, then you can get confused, you can get lost, because you'll hear people say things like, oh, it's only 1 degree of warming. But 1 degree of warming is enough to shut down ocean currents, collapse coral reefs, and cause the extinction of species. So, you have to make sure numbers carry weight. When we talk about global increase in temperature, 1 degree is a significant amount. 2 degrees is said to be high enough to collapse our entire ecosystem. So what are some of the changes from global warming? Right, so there's some of the obvious ones you may know about. Earth gets warmer, you're going to have the melting of glaciers and ice caps. That'll be associated with a rise in sea level. So our coastlines will start to become eaten away by waves. We'll have shorter winters, and these are things we're already experiencing. Species distribution shifts, so animals going extinct or moving into areas that were previously colder, but now since they've warmed up, the animals are moving with the climate, right? And you'll see sea surface temperature increases, hotter, earlier summers, more severe droughts, wildfires, water contamination issues, and the ecosystem changes and extinctions. So, it's not my favorite lecture to teach because it's so apocalyptic, and usually students have a hard time accepting it. But I think you guys are better off than previous classes, because you have an appreciation for how vulnerable humans are, right? We're living through that right now. So when we talk about changes on our planet, right, we can see how just a really small change can affect the whole world. So sea surface temperatures have risen since 1970, which means that we have increased hurricane activity. So, up until 2015, before that time, hurricanes had a season, right? They'd only appear during certain times of the year. But now we're seeing hurricanes occurring all over the world at all times of the year. And we're also seeing an increased number of the strength of those hurricanes, but of more 4 and 5. So last year we saw a record number of category 4 and 5 hurricanes. So we're seeing more hurricanes, and they're also more intense and stronger hurricanes. If we look at the ice cap, so here we have a picture. This red line here indicates the extent of the ice sheet from 1979 to 2000. So from 1979 to 2000, the ice sheet took up this amount of space. And you can see here how much has been lost in 20 years. So since 2000, we've lost this much ice, around half. So in only 20 years, we've lost half of our ice sheet. That rate is unprecedented and has climate scientists obviously very horrified. And the reason why things tend to move so fast now as opposed to before, post 2000, things are moving a lot faster, because as Earth gets warmer, it ignites these loops called positive feedback loops. So remember we talked about albedo, right? How ice has the highest albedo, meaning that ice reflects the most solar radiation back into space, whereas land and ocean will absorb more of that solar radiation without reflecting it back. So as we lose more and more ice, where Earth is also losing at the same time its ability to reflect back that solar radiation. So it's a double fold increase. So that's, I think, the hardest thing for normal people to grasp who've never taken a science class, is that Earth is a really complex climate system. And, you know, it's hard for people to envision, well, how could humans cause such enormous changes? It's because it only takes a little change to trigger Earth's own enormous internal changes that it has. So we're going to look at some of those, and on your test you'll have to describe to me those positive feedback loops. So that's one example of a positive feedback loop: the interaction between the warming of the planet and the ice cap's ability to radiate heat back into space. The more you warm the planet, the more ice you melt, and the less ice you'll have to reflect radiation, making the planet warmer. Okay, so another positive feedback loop, in addition to the polar ice caps, is the changes that we'll see in the oceans. So next week I'm going to offer an extra credit assignment, and you can choose to watch one of several different documentaries and do a report on that. So I'll have you give me your one-on-one summary of what you observed in the documentary. And one of those is called Chasing Coral, and I always have a lot of students tell me they love that one a lot. They like the main character. He's kind of a goofball. He's obsessed with coral. But basically, when we have a warming planet, when we warm the oceans, some atmospheric carbon dioxide will dissolve into the ocean water, and that acidifies the ocean. So the ocean becomes more acidic, like an acid. And if you know anything about acids from a chemistry class, you know that they're corrosive, right? And so because the ocean is becoming more and more corrosive, it's going to threaten the calcifying organisms that utilize calcium carbonate for growth of their hard shells. So things like our corals. And you guys are probably very familiar with the fact that the corals are going extinct. And probably they will be extinct in the next couple of years, 2 to 3 years. So there's this huge effort, and so I recommend that documentary to preserve the corals and to stop global warming, because the corals are basically like the rainforest of the ocean. They provide us a substantial portion of Earth's oxygen, and they also help regulate global warming. So if they die, then we lose yet another means for that. So a positive feedback loop that you can describe from here is called ocean acidification. So as you input carbon dioxide into the atmosphere, some of that is absorbed by the ocean. And as the ocean warms, it becomes more acidic. As it becomes more acidic, it dissolves these calcifying organisms. So when the coral shell dissolves, it releases that carbon dioxide gas back into the ocean. So all of these corals and these marine organisms, when they die, their shells go down to the bottom of the ocean and they pile up and they eventually compress together to form rocks known as limestone. And that limestone is weak to carbonic acid, and it will dissolve with a warming ocean. And right now, those ocean rocks, those limestones, are storing a majority of Earth's carbon dioxide. And so if we start to dissolve that, we are releasing all of this carbon dioxide that's basically been trapped in there. So humans disturbed the natural proportion of carbon dioxide in the atmosphere, and as a result, that change caused multiple other changes in the natural system. So it generated these positive feedback loops that feed back into the initial change. So that's how you can understand the impact that humans have, is that it's accentuated by Earth's natural mechanisms. but those mechanisms could be subsided if humans weren't altering the climate. Okay, so you can see that summed up here, feedback loops. Make sure you know this for your exam next week. And I will give you guys plenty of time to work on the exam. I'll leave it open all week. And you guys will have the same time as you did before. But basically, a positive feedback loop is where you have an increase in A. So that could be the amount of carbon dioxide, leads to an increase in B, which is temperature, right? So remember, if we increase greenhouse gas, then the temperature goes up because we have increased our ceiling of our greenhouse. And that increase in B, the warming, leads back to an increase in carbon dioxide. So you can think about it as humans increase carbon dioxide, this warms the planet, and then the warm planet releases more carbon dioxide. Because the planet thinks that it's retreating from an ice age, right? We've triggered this feedback mechanism in Earth's natural system through our own stimulation here. So we'll look at this in the next lecture too. I'll pull up Google Earth and we can kind of tour around and look around the world and see what areas have the fastest rising sea level. But the main contributors are the melting of the Antarctic and Greenland ice sheets, and is associated with the thermal expansion of ocean surface waters. So those are the two things, right? We're melting ice, and then the warmer temperature means that the water will expand, right? Because remember, we learned in our previous lecture on ocean-atmosphere interactions, cold stuff contracts, warm stuff expands. So here's that global sea level rise curve here. So the red line indicates sea level. So here you can see change in mean sea level in millimeters. And here's the year, 1984, going to 2008. So you can see sea level goes up and down, up and down, up and down, right? But over a long period of time, right, from 1994 to 2008, we can see it has increased. So that's that black trend line they've drawn through the data. So why does it go up and down in the short term? Why does sea level go up and down in the short term? Well, that has to do with the seasons, right? So in the winter time, there's more ice, and in the summertime, there's less ice. There's a slight natural variation to sea ice cover based on the seasons. But you can see overall, the overall trend is increasing very rapidly. And that's just from 94 to 2008. Okay, so now let's take a look at this other video that I have. Yes, this is the one.
From pollution to overpopulation are driving up the Earth's temperature and fundamentally changing the world around us. The main cause is a phenomenon known as the greenhouse effect. Gases in the atmosphere, such as water vapor, carbon dioxide, methane, nitrous oxide, and chlorofluorocarbons, let the sun's light in, but keep some of the heat from escaping, like the glass walls of a greenhouse. The more greenhouse gases in the atmosphere, the more heat gets trapped, strengthening the greenhouse effect and increasing the Earth's temperature. Human activities, like the burning of fossil fuels, have increased the amount of CO2 in the atmosphere by more than a third since the Industrial Revolution. The rapid increase in greenhouse gases in the atmosphere has warmed the planet at an alarming rate. While Earth's climate has fluctuated in the past, atmospheric carbon dioxide hasn't reached today's levels in hundreds of thousands of years. Climate change has consequences for our oceans, our weather, our food sources, and our health. Ice sheets, such as Greenland and Antarctica, are melting. The extra water that was once held in glaciers causes sea levels to rise and spills out of the oceans, flooding coastal regions. Warmer temperatures also make weather more extreme. This means not only more intense major storms, floods, and heavy snowfall, but also longer and more frequent droughts. These changes in weather pose challenges. Growing crops becomes more difficult. The areas where plants and animals can live shift, and water supplies are diminished. In addition to creating new agricultural challenges, climate change can directly affect people's physical health. In urban areas, the warmer atmosphere creates an environment that traps and increases the amount of smog. This is because smog contains ozone particles, which increase rapidly at higher temperatures. Exposure to higher levels of smog can cause health problems such as asthma, heart disease, and lung cancer. While the rapid rate of climate change is caused by humans, humans are also the ones who can combat it. If we work to replace fossil fuels with renewable energy sources like solar and wind, which don't produce greenhouse gas emissions, we might still be able to prevent some of the worst effects of climate change.